Ever wondered how to predict the next term in a sequence using a mathematical formula? Welcome to the world of recurrence relations. These are a fascinating concept in mathematics that allows us to define the nth term of a sequence based on the previous terms. Imagine a sequence of numbers, each term intricately connected to the ones before it, following a specific rule or formula. That's what recurrence relations are all about. They are not just arbitrary rules, but rather, they are the heartbeat of many sequences in mathematics. They often involve a fixed number of previous terms, a feature we call the order of the relation. From the simple sequences we learned in school to more complex ones like the Fibonacci sequence, recurrence relations are the hidden machinery that drives them. So, in essence, recurrence relations are mathematical tools for predicting the future of a sequence. Recurrence relations are not just abstract concepts. They have real-world applications too. Take population growth prediction, for instance. It's a classic example where recurrence relations come into play. Biologists use them to predict the number of individuals in a population over time, considering factors like birth and death rates. Another fascinating application is financial forecasting. Economists and financial analysts use recurrence relations to predict future economic trends based on past data. They can forecast stock prices, inflation rates, or even the GDP of a country. And let's not forget the realm of computer science. Algorithm analysis is a field that heavily relies on recurrence relations. They're used to determine the running time or space complexity of algorithms, especially recursive ones. This helps programmers optimize their code and make it run more efficiently. As you can see, recurrence relations have a wide range of practical applications. They're not merely mathematical puzzles, but tools that help us understand and predict the world around us. When dealing with recurrence relations, one crucial concept is the order. Now let's get into the nitty-gritty of it. The order of a recurrence relation refers to the fixed number of previous terms it involves. In other words, it's like a stepping stone that helps us determine the current term based on a certain number of preceding terms. For instance, a first-order relation would involve just one previous term. A second-order relation, on the other hand, would involve two previous terms, and so on. It's like climbing a ladder, where each rung represents a term, and the order tells us how many steps we can take at a time. So, if we understand the order, we can predict the next term in the sequence with ease. This concept is not only fascinating, but also forms the backbone of recurrence relations. Understanding the order is key to working with recurrence relations. Now, let's dive deeper and explore a specific type of recurrence relations: linear recurrence relations. Linear recurrence relations are fascinating. They define the nth term of a sequence as a linear function of its previous terms. Intriguing, isn't it? Take the Fibonacci sequence, for example. Each term in this sequence is the sum of the two preceding ones. From 0 and 1, we get 1, 2, 3, 5, 8, and so forth. Here, the nth term is a function of the n1th and n2th term. This is the beauty of linear recurrence relations. They form a bridge, a connection between terms in a sequence, linking each term to its predecessors in a structured mathematical way. Think of it like a relay race. Each runner, or term in our case, takes the baton from the previous one, adds their effort, and passes it on to the next. So, linear recurrence relations are all about connections between sequence terms. But how do we solve these recurrence relations, you might ask? Well, it's a fascinating process that involves transforming these relations into closed-form expressions. This transformation, in essence, is the solution to the recurrence relation. So let's take a quick dive into this process. The goal is to find a formula that can predict the nth term of a sequence without needing to know the previous terms. It's like having a roadmap to any point in our sequence, without having to traverse the entire path. A closed-form expression for a sequence defined by a recurrence relation is not always easy to find, but when we can, it's a powerful tool. It helps us to decode the pattern of the sequence and predict future terms effectively. This is particularly useful in algorithm analysis, where recurrence relations often arise. By solving these relations, we can understand how our algorithms will perform in the future based on their past performance. So, the next time you come across a recurrence relation, remember, it's not just a sequence of numbers. It's a puzzle to solve, a code to crack. Solving recurrence relations allows us to predict the future of a sequence with accuracy. Having understood recurrence relations, let's now move on to another fascinating concept: composition of relations. This concept is like a master chef who combines different ingredients to create a new dish. Here, the ingredients are the relations, and the dish is the new relation we get after the composition. In the world of mathematics, a composition of relations is a process that combines two or more relations to form a new one. It's like a chain reaction, where one relation leads to another, creating a whole new connection. This composition is not just a random combination. It's a well-structured process that follows certain rules. It's like a dance, where each step is connected to the next, creating a beautiful pattern. So composition of relations is all about creating new relationships from existing ones. It's like building a bridge between two islands, connecting them to form a larger land. And just like a bridge, the composition of relations helps us understand and navigate the intricate world of mathematics. Before we delve deeper into composition of relations, it's important to understand binary relations. A binary relation is a connection between elements of two sets. Picture two groups of objects and lines drawn between some objects from each group. That's a binary relation, showing how certain objects are related. In the realm of mathematics, binary relations are everywhere, from equalities and inequalities to more complex relations. They also play a crucial role in composition of relations, where we connect relations to create new ones. Binary relations form the foundation for understanding composition of relations. So how do we compose relations? Let's break it down into manageable steps. First, we identify two relations that we want to compose. These relations can be any two sets of ordered pairs. Now we're looking for a connection, a kind of bridge between these two relations. We're searching for a common element in the second position of the first relation's pair and the first position of the second relation's pair. Once we find this common element, we create a new relation that connects the first element of the first pair to the second element of the second pair. This is our composed relation. It's like a relay race, where the baton is passed from one runner to the next, creating a link from start to finish. As you can see, composing relations involves a systematic process. Composition of relations, like recurrence relations, also have real-world applications. Let's dive into a few examples. In social network analysis, composition of relations is used to map relationships between individuals, groups, or even entire networks. Think about your favorite social media platform. How do they suggest new friends or pages to follow? They use composition of relations to draw connections based on shared interests, mutual friends, and more. Moving on to database management. Here, composition of relations helps to ensure data consistency and integrity. By defining relationships between different data entities, we can easily retrieve, manipulate, and manage data in a reliable manner. And let's not forget about artificial intelligence, which relies heavily on composition of relations. It's used in machine learning algorithms to predict outcomes, recognize patterns, and make decisions based on data inputs. In essence, composition of relations play a crucial role in understanding complex systems. Now that we know the theory, let's solve a problem involving recurrence relations. Imagine we have a sequence defined by a recurrence relation, such as the nth term of the sequence is equal to twice the previous term plus 1. Let's say the first term is given as 2. Now, to find the second term, we simply substitute the first term into the recurrence relation. So, twice 2 plus 1 gives us 5. Now, to find the third term, we substitute the second term into the relation. Twice 5 plus 1 gives us 11. If we continue this process, we can generate the whole sequence. But what if we want to find the 100th term without finding all the previous terms? This is where the solution of the recurrence relation comes in handy. By solving the recurrence relation, we can get a closed-form expression for the nth term, which enables us to directly calculate any term of the sequence. Solving problems like these helps solidify our understanding of recurrence relations. Let's now solve a problem involving composition of relations. Imagine we have two relations, R and S, defined on a set. The composition of these relations, denoted as R composed with S or ROS, is a new relation that associates elements which are related by a chain of two links, one from R and one from S. To solve a problem involving the composition of relations, we first identify the pairs in relation R and S. Then, we look for a common element in the second component of a pair in R and the first component of a pair in S. If such a common element is found, we create a new pair linking the first component of the R pair to the second component of the S pair. This process is repeated for all pairs until no more new pairs can be formed. The set of all these new pairs constitutes the relation ROS, the composition of R and S. Solving such problems gives us hands-on experience with composition of relations. Let's do a quick recap of what we learned about recurrence relations. These mathematical constructs define the nth term of a sequence based on previous terms. The order of a recurrence relation refers to the fixed number of previous terms it involves. One common type is the linear recurrence relation, which equates the nth term to a linear function of preceding terms. We also touched upon solutions to recurrence relations that give us closed-form expressions. Remember, practice is key when it comes to mastering recurrence relations. Let's also recap the main points about composition of relations. We've explored how binary relations form the groundwork for understanding composition of relations. We've seen how the process of composition involves combining two relations to form a third. Real-world applications of composition of relations are plentiful, ranging from social networks to computer science. And remember, just as with recurrence relations, the secret to mastering this concept is practice. Keep practicing problems involving composition of relations to get better at it. We've learned a lot today, but why are these concepts important? The beauty of recurrence relations and composition of relations lies in their vast applicability, making them essential tools in a number of fields. Recurrence relations, for instance, are pivotal in computer science for analyzing the efficiency of algorithms, helping us understand how performance scales with input size. This is crucial for creating faster, more efficient software. In the realm of mathematics, these relations allow us to define complex sequences and structures in a simple, iterative way. This can help in cracking intricate mathematical problems or modeling natural phenomena. Then we have the composition of relations, a concept that's key in the study of functions and sets in mathematics. But beyond that, it has found a home in economics too, where it helps in understanding and analyzing complex economic models. So, mastering these concepts can open up a world of opportunities in various fields. As we wrap up, remember that both recurrence relations and composition of relations are powerful mathematical tools. They hold the keys to decoding complex patterns and relationships. Don't stop here, though. Keep digging deeper into these captivating concepts and practicing problems. The more you engage with them, the more they'll reveal their secrets to you. It's a journey of endless discovery. Keep learning, keep growing. Remember, the world of mathematics is full of fascinating concepts waiting to be explored.